Welcome to this HP Expert 1 presentation. This is the second video explaining the OSI model. In the first video, we looked at the reasons for the OSI model and the layers of the OSI model. In this video, we're going to continue the discussion by looking at traffic flows between hosts and a demonstration of the OSI model by capturing traffic using Wireshark. Let's get started. Now, when communication takes place between two hosts, in this example we've got host A talking to host B, the information that's going to be transmitted over the network must undergo a process of conversion at both the transmitting device and receiving device. This is commonly known as encapsulation and de-encapsulation, and I'm going to cover it in more detail in the next few minutes. At the end, you should be comfortable with the fact that each layer of the OSI model only communicates with the corresponding layer of the communication partner. In other words, layer 7 communicates with layer 7, layer 1 with layer 1. So let's look at that in more detail. So when the sender wants to transmit data, let's say in this example, your PC is opening up a connection to hp.com and we're sending some information. That information has to go through the OSI model from layer 7 all the way to layer 1 to then be transmitted across the physical media. So in this case, user data is transmitted. So at layer 7 of the OSI model, the data is encapsulated with a layer 7 header. That in turn is encapsulated with a layer 6 header at the presentation layer. And that in turn is encapsulated with a layer 5 header at the session layer. And that in turn is encapsulated with a layer 4 header at the transport layer. And this continues all the way down. At layer 3, the data is encapsulated with a network layer header. At layer 2, the data is encapsulated with a data link layer header. And in this case, a frame check sequence is added to the data. This ensures that the data is not corrupted when sent from the sender to the receiver. Lastly, the data is transmitted across the physical wire or physical media as bits, in other words zeros and ones, and that is then sent from the sender to the receiver. What I'd like you to notice here is that each layer of the OSI model prepends a header on the data. So data is encapsulated with a layer 7 header all the way down to the lower layers of the OSI model. And then it's transmitted across the wire. In a moment, I'll demonstrate this by using Wireshark, which is a great sniffing application to view data in real time. But for now, please notice the sender is transmitting data. The data is encapsulated at each layer of the OSI model and is then transmitted to the receiver. So A is sending the data to B. This is a very simple network where I've got two PCs connected with, say, a crossover cable, but in the real world, the network between these devices could be really complicated. Device A may be in England and device B may be in the USA. And there's obviously going to be multiple devices and multiple media types when data is transmitted from A to B. But let's keep it simple for the moment. The data is transmitted across a single cable from A to B. At the receiving end, the receiver reverses the process. So the bits are received at the physical layer by the network interface card. The layer 2 header is read. It's then stripped and the data is passed to layer 3. The layer 3 header is read and that's stripped and passed to layer 4. And this process continues until all the headers have been removed. So this is a process of de-encapsulation where the headers are stripped and the data is passed up through the OSI model until only the original data remains without any headers. This data would then be used by an application on that PC, in this case perhaps a web server, and that data would then be processed by that web server. So in summary, please note, on the sender, the data is transmitted down through the OSI model and encapsulated at each layer, and then physically transmitted across the wire. At the receiver, the data is de-encapsulated at each layer of the OSI model until we have the original data, which is then used by the application. What's important to note is that because of encapsulation and de-encapsulation, each layer of the OSI model only communicates with the equivalent layer on the other device. So in this example, PCA's application layer communicates with PCB's application layer. The same is true for all the other layers. Presentation communicates with presentation layer, session with session, transport with transport, and so forth and so on. Each layer communicates only with the equivalent layer on the other device. At the physical layer, the data is transmitted as bits. So as an example, if we used Ethernet, electrical current may be used to transmit zeros and ones. Now, specific terms are used in networking to refer to each layer. So at the physical layer, the data transmitted is known as bits. At the data link layer, it's known as frames. At the network layer, it's known as packets. And at the transport layer, it's known as segments. So in other words, PCA transmits packets to PCB at the network layer. At the data link layer, for example, frames are transmitted, and so forth and so on. It's important that you understand these terms, because in networking, we're going to discuss how packets are transmitted between routers or how frames are transmitted between switches. Routers reside at layer 3 of the OSI model, and switches reside at layer 2. These days, those lines are blurred because we have layer 3 switches, but in simple terms, a router would transmit packets and a switch would transmit frames. Now, in the real world, a lot of network engineers do not use the OSI model in its purest form or original form. Network engineers tend to concentrate on the lower 4 layers of the OSI model. Now, that's changing again with the rise of virtualization and converged infrastructure, but it's still true for many network engineers. So the OSI model in its purest form had 7 layers. We had the application layer at layer 7 all the way down to the physical layer at layer 1. This model, however, was not originally developed for TCP/IP. It was originally developed for protocols such as CLNS and CLNP, or connectionless mode network service and connectionless mode network protocol. Don't worry too much about these protocols. Unless you're using a routing protocol such as ISIS, they're not used very often. TCP/IP had its own model, which consisted of the application layer, the transport layer, internet layer, and network access layer. So as you can see, the top 3 layers of the OSI model, application, presentation, and session, are grouped together into the application layer. The transport layer is equivalent. The network layer is known as the internet layer, and the data link and physical layer were grouped together into what's called the network access layer in the TCP/IP model. In the real world, we tend to use a hybrid of these 2 models. So we often group the application, presentation, and session layer into the application layer, but we still refer to the transport, network, data link, and physical layers, which are part of the OSI model. The reason for that is that we as network engineers tend to spend most of our time looking at the lower 4 layers of the OSI model, and thus the top 3 layers are grouped together into a single layer known as the application layer. Our time tends to be concentrated on getting data or information from one host to another host. The higher layers of the OSI model may be the realm of a developer or server admin, and thus a lot of network engineers will use the hybrid model but still refer to it as the OSI model. So just be aware that we have the pure OSI model, we also have the TCP/IP model, and then we have this hybrid model. However, because of converged infrastructure and the growth of VMware, a lot of network engineers are having to work with all the layers of the OSI model. So this may not be true in your environment. You may be troubleshooting applications, whereas other network engineers never get involved with application troubleshooting. Another important concept to understand is that when host B receives traffic, it needs to have some kind of reference to know which protocol is being used at higher layers. So as an example, A might be sending telnet traffic to B, but at the same time, it may be sending TFTP traffic to host B. How does it know which of these applications that traffic belongs to? Because you could have telnet traffic arriving and then TFTP traffic and then more telnet and then more TFTP. This device may also be running multiple layer 3 protocols. So as an example, it may be running IP version 4 as well as IP version 6. How does it know whether the traffic arriving at layer 2 is IP version 4 or whether it's IP version 6? So when the bits arrive at the physical layer of the network interface card of a PC, it'll read the layer 2 frame at the data link layer, and in that frame, if it's using Ethernet 2, which is the most common type of Ethernet, there's a field called the type field that denotes or specifies the higher layer protocol. So the type field will inform the device if IP version 4 is being used or if IP version 6 is being used, or some other protocol such as IPX. So the type field informs the device which process is being used at higher layers, IPv4 or IPv6. At layer 3, the protocol number informs the device which protocol is running at layer 4. The two most common protocols are TCP and UDP. So at the network layer, the protocol field specifies the layer 4 protocol. And at layer 4, the port number specifies the application that's being used. Is it telnet? Is it TFTP? Is it HTTP? And so forth and so on. So as an example, telnet uses port 23, TFTP port 69, HTTP port 80. And there are other well-known port numbers. It's well worth learning port numbers to help you in your networking career. But without further ado, let me demonstrate traffic sent from my local PC through a router to google.com. And let's capture some of that traffic and interrogate it, and then I'll explain the various layers of the OSI model in that Wireshark capture. Wireshark is a free network protocol analyzer or sniffer, and it will allow us to capture data that is transmitted and received by my PC and show us really nicely the different layers of the OSI model. So the first thing I need to do, go to capture and then specify the interface that I want to capture traffic from. So in this case, I've got my local NIC card. I'll be able to see packets that are transmitted and received. I can then select my interface, in this case, my local network connection. I can then go to a website such as google.com. Wireshark will capture those packets and all other traffic on my network card. In this case, I've set it to promiscuous mode. Promiscuous mode will allow me to capture traffic not destined to my PC. But at this point, I'm going to go capture, stop to stop the capture. I can now filter the information in Wireshark, so I'm only going to look for HTTP traffic. In this example, you can see that I've received traffic from Google. Notice the IP address 74.125.233.82, and it's being sent to my IP address 10.0.0.5. Now looking at the frame, we can see that 777 bytes were captured. This is an Ethernet 2 frame, which was sent by my local router, in this case it's a Cisco router, to my local PC. Here's the MAC address of my PC, here's the MAC address of the Cisco router. What I'd like to point out here is notice the type field, specifying that the protocol used at layer 3 is IP version 4. So the type field for IP version 4 in hexadecimal is 0800. At layer 3, you can see that we're using version 4 of IP. Notice the source and destination IP addresses. A huge amount of information can be gleaned from this Wireshark capture, and I won't bore you going through all the options. But notice here we can see differentiated services code points, or DSCP, which is used for quality of service. What I want to point out here is notice the protocol used at layer 4 is TCP. So the protocol number for TCP is 6. At layer 4, we can see that TCP is being used. You can see the source port being 80. Google is sending traffic back to my PC. 80 is a well-known port number, and this is my ephemeral port, which is just used for this session. I initiated the session to Google, so I initiated it from a random port number to a well-known port number. Port numbers are explained in more detail in the TCP video. Other information with regards to TCP can be seen here. Notice, for example, the sequence numbers. TCP uses sequence numbers to ensure that traffic has been received correctly. Notice the acknowledgement. Window size is the amount of data that can be transmitted without receiving an acknowledgement. You can see the segment size is 723 bytes. If we look at the higher layer protocols, notice we've got HTTP here, and digging into the HTTP, you can see that the data was compressed using gzip. And if we look at the actual HTTP itself, you'll be able to see that this information came from google.com. Google does a lot of tracking, and as you can see here, there's a lot of information transmitted from that very basic Google page. But as an example, you can see google.com referenced multiple times in the HTML. Notice as an example, the end of the script, end of the body, end of the HTML. So, with Wireshark, we can capture data from the wire and interrogate it to see what's going on. So just in summary, this is IP version 4 as an example. High layer protocols are referenced within lower layer protocols. And you can see quite nicely layer 2 of the OSI model, layer 3 of the OSI model, layer 4, and then the higher layers being the application layer. That concludes this video discussing the OSI model. In this video, we looked at the different layers of the OSI model. So starting at layer 1, the physical layer, layer 2, the data link layer, layer 3, the network layer, layer 4, the transport layer, layer 5, the session layer, layer 6, the presentation layer, and layer 7, the application layer. I explained the difference between the OSI model and the TCP IP model. I demonstrated the OSI model by using a Wireshark capture to show you the different layers, and I explained how the layers interact with one another. For more information, please go to hp.com/go/expert1.